Okay, troops. I'm here to show you a couple of simulations that can help you understand what's going on with a ballistic pendulum. Yeah, normally I provide PDF, but if I don't get to it, it just go to Wikipedia, and there's a really great article there. Just realized it's not there, but in the module. But what is there are three simulations, and so the first two you would use is this projectile concepts and energy concepts, and then the quiz part we'll get to in a minute. So in principle, when you click on projectile concepts, you'll come to this PhET site. I actually forgot what PhET stands for, but the University of Colorado in Boulder, where my wife was born, has provided these, and it's pretty cool. And there's different options down below. I thought that the link would bring you here, and if I recall, it'll start out something like this. And I encourage you to play games. It's kind of fun. There's a variety of projectiles available. You can see where physicists can be kind of whimsical. But let's see. And then you can adjust the angle here. You can adjust the initial speed of the projectile. And so, see, you get different effects. You can adjust the strength of gravity. You can add air resistance. But those aren't air resistance the way we've set up the lab, the way the lab equipment is set up. Similar to Galileo and our air track, so make a note to yourself that you want to verify the concepts about air resistance, because of course we don't put on spacesuits and pump the air out of the room. We do things to make sure our equipment is as immune to this as we possibly can make it. So you can really make the thing zip along. So at the end of the day here, the thing that we're mostly interested in is something like this, because that's what I did that too soon, so clear off those old tracks. And so, one thing else I wanted to show, so let's just reset this. So that thing goes off, and we have a couple of instruments here. I'm not sure exactly what to do with that one. I guess you could measure. Now you see this little toy can get you everything. One other thing you can do is you can set the bullseye or do a measurement, although they kind of want you to predict where to put that. But look, at this thing is cool. So you put on any one of the dots, and it'll tell you how much time it took to get there. The range is the x-coordinate, and the height, of course, is the y-coordinate. So you can study things about the trajectory of the projectile. Okay, so let's reset that one more time. So we'll simulate our ballistic pendulum, which is going to be on the table. It's going to do, the ballistic pendulum is going to do two things. You're going to shoot the projectile into it's not exactly a wood block, but you're going to shoot it into this catching mechanism, and it's going to, once the bullet, which is it's a steel ball, once it hits, it's going to be captured, similar to what we see here, and it's going to swing up, but what we have, it's going to have a mechanism to stop it. So then we'll be able to measure this height. And then at some point, hopefully, you'll figure out what would be the angle theta. We are going to be just dealing with the height part, but it's in this h, and you can see I helped you out by putting some labels in here. The determining of theta and the height itself are all part and parcel to the way a ballistic pendulum works in the first place. So once you've done that part, you're going to use that. Well, let's do it then. This part is going to tell you what the energy is. So let's go to this sim. So you click on the energy part of the sim, and I put it just even in the intro. There's friction and there's playground, and please go ahead. I mean, it's fun. You can create your own roller coasters here. I think you can just keep you can just keep adding to it. So you can do some crazy stuff if you like, and it's fun. Anyways, let's take our gal here. Oh yes, and we should have the bar graph, the grid, and the speed. Now, if we put her at a particular height, you see the little red dot, and we shoot it, notice how she comes back up to the same height. Also notice where her maximum speed is. It's right on the right at the bottom. And since there's no friction, it just keeps going on and on. And one thing to take note of is that if we stop this, and you can also do it in slow motion, notice that before she starts, and for the energy, there's no kinetic energy because I stopped her, is only dependent upon how high she is. So that's a key concept. And notice that if I started her off here just below 2, she's going to be trapped in that well. So in order to get her out of that well, I have to start her out someplace that's a little bit higher. And also, again, notice where her highest speeds are. And she only goes back up as high as she started at. So now we go back to here. This is sort of the basic concept of the one part of the ballistic pendulum. And it's mostly what happens is I can't do it with this sim. In the ballistic pendulum, what we're doing is we're going to give her an initial speed. And then basically, by the swing of the pendulum, how high it goes, notice how that is the potential energy. So basically what we're going to do is we're going to turn potential energy into, kinetic energy into potential energy. And there's a concept of conservation of energy is that the two remain equal. Watch this total energy bar here. It stays constant, and it really only it does change if there's friction. But again, we're setting things up so as to minimize the effects of friction. I don't know. No, we can't set her initial speed. Okay, that's too bad. That's what I wanted to show you. So in this case, it's basically something like this. Also, it's just half of it. The thing is, again, I can't give her an initial speed, but I can put her at a certain place. And you can notice I started at 4. Notice the speed is just before that center hash mark. So if I put her back here at 4, and we should see, see that's the maximum speed. All right, so that's the first part of using the ballistic pendulum. And then the next part is you're going to shoot the ball across the room, and you need to measure where it lands. And in the case that we have, it's going to also, we're going to shoot it out horizontally. So that's why I have it set up here at 0 degrees. We need to measure the height of our table, and most particularly, not just the height of the table, we need to measure where is, and you'll see the apparatus when we get in there. We have to measure the height of where the ball is released. And then notice that we already know what the range is. It's 25.7. But the critical thing to notice here is the time it takes. And we can decrease the initial speed. What I want you to do is measure how much time it's taken to get there. And then the real key is I can shoot it with 0 speed. And it just drops. And in all cases, I want you to notice what is the time it took to get where it's going. And what's nice about horizontal projectiles, once you understand the time, then you understand quite easily where it's going to land. And you can also do something like this. You can take this thing and now set it at a different height and launch it at the same speeds. Notice that it went a little further, and now if you measure the amount of time it takes to go to the ground, you'll see a similarity. In fact, here's what I would urge you to do. Take this thing, say set it at 10, and then set, let's say 0, 5, 10, 15. Oh, yeah, where's 15? It should be enough. Okay, so now you've got 1, 2, 3, 4. Measure the time and take note of how far it goes for each speed. So we had 0, 5, 10, 15. Find out the time, and then move this to a different height. Let's say 15 might go off the page. All right, so now you do the same thing. Well, we have to clear it. That's a pain in the butt, but we can just do. In fact, if we do 5 meters, it gets even easier because it's half the height. Well, that's not strictly true, but it's still easier. Does it matter? What's easier to do? Let's put it at 8 meters. And then once again, 0, 5, 10, 15. Take a note of the time in the air, how long, that time in the air, how far it goes, and the initial speed. And you should be able to figure out a relationship. It's pretty straightforward. And in fact, it's totally related to this and the way the ballistic pendulum, what the ballistic pendulum lab that you're doing, there's a relationship between that speed and then the speed she has at the bottom here. You think about putting her up here as pulling the cocking spring back. You pull the trigger and she shoots out, and then she goes to a certain height, and remember I keep telling you, height has something to do with potential energy in this case. But once potential energy is height, kinetic energy is 1/2 mv squared, 1/2 mv squared, and which is, in this case, because it's squared, it's just the speed. And look at there, you have a speed there. So so you would also want to check out, and I suppose I'll have to add this to the pre-lab, Well, once you study the pre-lab, you'll see. I mean, a ballistic pendulum depends on potential energy and kinetic energy, and then we're going to add this part where we shoot the marble out vertically in a normal kind of cannon, and we're going to use the information from the pendulum part to predict where our marble's going to land. And so it's all these. When we're in lab class, it won't take very long to take data. But if you do this preliminaries, you'll be a leg up on the analysis. You probably can take off early, and I guess we'll do something like the we did last time with using Zoom while we were in class. That was kind of interesting. Okay, so remember, everything is here except for the actual Wikipedia article. Oh, and I'll have to add a playlist link for where this video is at. Okay, I'll see you all soon.